episode 66, titled STP Essentials, Why Loops Happen and How Designs Prevent Them, the focus is on spanning tree protocol as the protection mechanism that keeps Layer 2 networks from collapsing under their own redundancy. Layer 2 is attractive because it feels simple and automatic, but the moment you add redundant links, you create the possibility of loops, and loops behave differently than most other faults. The exam tests spanning tree protocol because it is one of the core concepts that separates a stable switch network from an unstable one, and because its failure modes are dramatic and easy to recognize if you know what to look for. Spanning tree protocol is not a performance feature, it is a safety feature, and it exists because Ethernet does not have a built-in loop prevention mechanism the way routing protocols do at Layer 3. If you can explain why loops happen, what they do to the network, and how intentional design prevents them, you can answer most spanning tree protocol questions reliably. This episode builds that understanding as a set of cause and effect relationships rather than as a collection of timers and state names. Before we continue, a quick note: this audio course is a companion to the CloudNet X books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A Layer 2 loop happens when there is more than one active path for the same frame to travel, and the network has no way to stop the frame from circulating. Unlike Layer 3 packets, Layer 2 frames do not have a time-to-live field that forces them to expire after a number of hops. That means a broadcast frame or an unknown unicast frame can be forwarded out multiple ports and then forwarded again by other switches, creating continuous circulation. The effect is amplified because switches flood broadcasts and unknown destinations by design, and a loop turns flooding into a self-sustaining feedback loop. Redundancy at Layer 2 is therefore both necessary for resilience and dangerous without control, because the same extra path that saves you during a failure can melt the network during normal operation. The exam expects you to understand that the loop is not limited to one link or one switch, but can cascade across a whole broadcast domain. It also expects you to recognize that loops often appear through human actions like patching mistakes, adding unmanaged switches, or creating unexpected interconnects. When you think of loops as uncontrolled circulation without hop limits, the need for spanning tree protocol becomes obvious. The effects of loops are severe, and three of the most common are broadcast storms, media access control flapping, and outright outages. A broadcast storm is a flood of broadcast traffic that consumes bandwidth and switch processing, preventing legitimate traffic from being delivered. Media access control flapping occurs when a switch learns the same source address on different ports repeatedly because frames are arriving through the loop from multiple directions, causing the forwarding table to oscillate. This flapping breaks connectivity because the switch keeps changing where it believes the destination lives, leading to misforwarding and drops. Outages occur because control plane resources are consumed, link buffers overflow, and even devices that are not directly part of the loop experience degraded service due to the shared broadcast domain being saturated. The exam often describes symptoms like high broadcast traffic, widespread packet loss, and unstable connectivity, and the correct diagnosis is often a Layer 2 loop. These symptoms can appear suddenly and affect many devices at once, which is a clue that the problem is not a single host or a single link. Loops can also trigger repeated topology change events, compounding instability as switches keep recalculating and flushing tables. When you can connect storm, flapping, and outage to a loop, you can identify the failure pattern quickly. Spanning tree protocol prevents loops by blocking redundant links, creating one logical tree that provides a single active path between any 2 points in the Layer 2 topology. The idea is not to eliminate redundancy physically, but to eliminate cycles logically by placing certain ports into a blocking state so they do not forward frames. When the topology is loop-free, broadcast and unknown traffic can still be flooded, but it does not circulate indefinitely because there is only one active forwarding path through the tree. If a primary link fails, spanning tree protocol can unblock a previously blocked redundant link, restoring connectivity while still maintaining a loop-free topology. This is why spanning tree protocol is often described as enabling redundancy safely, because it allows you to wire more than one path, but keeps only one active at a time for a given segment. The exam expects you to understand this blocking behavior as the core mechanism, not as a minor detail. It also expects you to recognize that the tree is a logical construct that must be consistent across switches, which is why route selection matters. When you think of spanning tree protocol as building a single logical tree out of a graph, the design intent becomes clear. Designing with intentional redundancy and predictable route selection is essential because spanning tree protocol behavior depends on which switch becomes the route and how paths are chosen. The route is the logical center of the spanning tree, and path costs are calculated relative to it, determining which links forward and which links block. If route selection is left to defaults, the route may be chosen unpredictably, such as an access switch becoming route, which can create suboptimal paths and make failures more disruptive. Predictable route selection means deliberately configuring the intended distribution or core switches to be the route for the relevant Layer 2 domains, so traffic follows expected paths. This reduces latency and avoids scenarios where traffic takes unexpected detours through access layers. The exam often tests this by asking where the route should be placed, and the correct answer typically places it in the distribution layer where aggregation and policy boundaries live. Intentional redundancy also means designing where blocked links will exist so that failover is predictable and does not require a full topology reshuffle under stress. When redundancy and route are intentional, spanning tree protocol becomes a controlled mechanism rather than a surprise generator. Edge protections like portfast and guard features exist because many of the worst loop events originate at the edge, where users and non-standard devices connect. Portfast is the conceptual idea of allowing edge ports to transition to forwarding quickly because end devices do not create loops in normal circumstances, and waiting for full spanning tree convergence delays connectivity unnecessarily. Guard features are conceptual protections that prevent edge ports from accidentally participating in topology roles they should never hold, such as becoming a path for a bridge device. These protections can also shut down or block a port when unexpected spanning tree behavior is detected, such as receiving bridge protocol messages on an edge port. The exam expects you to understand the purpose of these features, even if it does not require you to list every vendor implementation. The purpose is to keep the edge stable, to prevent accidental loops, and to reduce the blast radius when a user plugs in an unauthorized switch or creates a patch loop. Edge protections are an extension of the principle that the network should treat user-facing ports differently than infrastructure interconnects. When you understand that edge ports are where mistakes happen, these protections feel like good hygiene rather than optional tuning. A common scenario is a user connecting a small switch and unintentionally causing a loop, which can happen when the user patches multiple wall jacks into the same switch. In that case, the user's switch creates a loop through the building cabling and the access layer switch, turning two edge ports into a cycle. The user may do this innocently, such as trying to extend network access to multiple devices without realizing that connecting two ports into the same Layer 2 domain creates a loop. The result can be immediate broadcast storm behavior and widespread connectivity problems for the whole VLAN. Spanning tree protocol can protect the broader network by blocking a redundant path, but if unmanaged switches behave unpredictably, or if edge ports are not configured with protective features, the loop can still cause disruption. The exam tests this scenario because it illustrates how simple actions at the edge can have campus-wide impact in Layer 2 environments. The correct reasoning is to combine spanning tree protocol with edge protections and physical controls to reduce the chance of loops being created. When you can explain how a user action creates a cycle, you understand why edge policy matters. Unmanaged switches are a pitfall because they can create unexpected spanning tree behavior or fail to participate in a predictable way, making loop prevention less reliable. Some unmanaged switches may pass bridge protocol messages, some may filter them, and some may implement limited or non-standard behavior, leading to inconsistent topology control. They can also introduce extra links that were not documented, such as when someone chains switches under a desk or in a ceiling space. These devices can change the effective topology without anyone realizing, and they can create loops through mismatching or accidental dual connections. The exam tests this by describing mysterious loops or unexpected topology changes and hinting at unauthorized or unmanaged switching devices in the environment. The correct response is to control what can connect at the edge and to configure switches so that unexpected bridging behavior on edge ports triggers protection rather than becoming part of the spanning tree. Unmanaged devices also complicate troubleshooting because you cannot inspect their state or logs easily. When you account for unmanaged switches as a realistic operational risk, you naturally design defenses that assume edge unpredictability. Route placement is another frequent pitfall because putting the route in the wrong place increases latency and can increase failure impact when topology changes occur. If an access switch becomes root, traffic between other access switches may traverse inefficient paths, sometimes climbing up and down through layers unnecessarily. It can also cause more links to block in places you did not anticipate, creating bottlenecks and reducing available redundancy. During failures, the spanning tree may reconverge in ways that move the route or change the active topology dramatically, leading to wider disruption and longer recovery. The exam often tests this by describing poor performance and instability during failures and asking what design choice would improve it, and correct route placement is often part of the answer. Predictable route placement also supports change management because you can anticipate which links are primary and which are standby. When the route is correct, the spanning tree aligns with the intended hierarchy rather than fighting it. Route placement is therefore an architectural decision, not a minor configuration tweak. Quick wins include locking down unused ports and documenting spanning tree roles so that the physical network cannot be easily looped and the logical topology is understandable. Locking down unused ports reduces the chance that someone creates a loop by plugging in unknown equipment or patching cables without authorization. Documentation of roles includes knowing which switches are intended routes, which links are intended to be blocked under normal operation, and how failover is expected to occur. This documentation turns troubleshooting from guesswork into verification, because when a link that should be blocking is forwarding, you know something has changed. The exam expects you to recognize that many Layer 2 failures are operational in nature, caused by unplanned changes and missing documentation. These quick wins also support audit and change control because they make topology changes visible and intentional. When you combine port discipline with topology documentation, you reduce both the probability of loops and the time to isolate them when they occur. This is practical resilience, not theoretical perfection. A key monitoring cue is to watch topology change events and excessive broadcasts, because these are strong indicators that the layer 2 topology is unstable or that a loop may exist. Topology change events indicate that the spanning tree is reacting to link state changes or reconvergence, and frequent events can signal flapping links, misconfigured ports, or loops causing instability. Excessive broadcast traffic is another warning sign, because stable networks have predictable broadcast levels, while loops amplify broadcast and unknown traffic rapidly. Monitoring should also include media access control flapping indicators if available, because repeated moves of addresses between ports are classic loop symptoms. The exam often expects you to connect monitoring observations to root cause, such as interpreting a sudden spike in broadcasts and topology changes as a likely loop event. These cues are valuable because they provide early detection before the network becomes completely unusable. Monitoring also supports evidence gathering during incident response, helping you identify where the loop might be forming based on which ports see the most anomalies. When you know what to watch, you can move faster during a crisis. A useful memory anchor is loop, storm, block, root, protect, edge, because it captures the life cycle of the problem and the main control points. Loop reminds you that redundant layer 2 paths create cycles that can circulate frames indefinitely. Storm reminds you that the visible symptom is broadcast amplification and widespread instability, often paired with media access control flapping. Block reminds you that spanning tree protocol solves this by blocking redundant links, converting a graph into one logical tree. Root reminds you that the tree depends on root selection, which must be intentional to produce predictable paths and stable failover. Protect Edge reminds you that many loops originate at user ports, so edge protections and port discipline reduce the chance of loops and limit their impact. This anchor is useful on the exam because it maps directly to diagnosis and prevention. Identify loop symptoms, confirm spanning tree behavior, verify root placement, and ensure edge protections are in place. When you can explain the anchor, you can explain the topic clearly without diving into vendor-specific commands. To diagnose symptoms that suggest a layer 2 loop, look for sudden, widespread degradation rather than isolated failures. You might see network-wide packet loss, high latency, and timeouts across many devices in the same VLAN or broadcast domain. You might see switches reporting high utilization on uplinks, rapidly increasing broadcast counters, and media access control tables changing constantly as addresses appear on different ports. You might see frequent topology change events and spanning tree reconvergence messages, indicating that the network is trying to stabilize but cannot. Users may report that connectivity comes and goes rapidly, and voice devices and cameras may drop in clusters rather than individually. These symptoms are consistent with a storm because the network's shared medium behaviors are being amplified by a loop. The exam expects you to recognize the pattern of broad impact and rapid onset, which distinguishes a loop from a single device failure. When you can connect the symptom cluster to loop behavior, you can choose the right mitigation quickly. A simple, plain order recap of prevention steps begins with designing redundancy intentionally and choosing a predictable route so the logical tree aligns with your hierarchy. Next, ensure edge ports are treated as edge ports, using protections that prevent unexpected bridging behavior and reduce the chance of user-introduced loops. Then, lock down unused ports and control what devices can connect, reducing accidental topology changes. After that, document which links should be forwarding and which should be blocking, so topology drift is detectable and troubleshooting is faster. Finally, monitor for topology change events, excessive broadcasts, and media access control flapping so you can detect instability early and respond before a storm takes down service. This order matters because it starts with architecture, moves to edge risk control, and finishes with operational visibility. The exam often rewards answers that reflect this layered thinking rather than focusing on one control in isolation. When you can state prevention as an ordered approach, you show that you understand both design and operations. It turns spanning tree protocol from a reactive mechanism into part of a proactive stability strategy. To close episode 66, titled STP Essentials, Why Loops Happen and How Designs Prevent Them, the central point is that spanning tree protocol protects Layer 2 networks by preventing loops that otherwise cause broadcast storms, media access control flapping, and widespread outages. Redundant links are valuable for resilience, but without control, they create cycles because Layer 2 frames do not expire as they circulate. Spanning tree protocol blocks redundant links to form one logical tree and unblocks paths during failures, but its behavior depends on intentional redundancy design and predictable route selection. Edge protections and disciplined port practices reduce user-introduced loops and prevent unmanaged switches from destabilizing the topology. Monitoring for topology change events and excessive broadcasts provides early warning and helps isolate loops before they become catastrophic. The pitfalls of unmanaged switches and poor route placement show how easily a stable design can become unstable if roles and controls are not deliberate. Your rehearsal assignment is a spanning tree role narration where you describe which switch should be root, which links should block under normal operation, and what should change during a single link failure, because that narration is how you demonstrate spanning tree protocol understanding in the way the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.